Article 680.74 of the National Electrical Code addresses the bonding requirements for hydromassage tubs. The core of the discussion revolves around proposed changes to the first sentence of this article, specifically concerning the type of conductor used for bonding. Proposal 1 suggests replacing the existing sentence with one that mandates a solid bonding jumper no smaller than number 8 American wire gauge. The rationale behind this proposal is that the current code language is unenforceable because it doesn't explicitly specify a solid conductor. This ambiguity could lead to the use of stranded conductors larger than number 8 American wire gauge, which may not align with the code's original intent. Proposal 2 suggests removing the word solid from the first sentence of Article 680.74 altogether. This implies that either a solid or stranded conductor would be permissible for the bonding jumper, as long as it meets the minimum size requirement of number 8 American wire gauge. Now let's delve into the arguments for and against each proposal, along with the underlying electrical engineering principles. The primary reason for requiring a bonding jumper in electrical systems is to create a low impedance path for fault current. This path facilitates the rapid operation of overcurrent protective devices, such as circuit breakers or fuses, in the event of a ground fault. A low impedance path ensures that a large fault current flows quickly, tripping the breaker or blowing the fuse, thereby disconnecting the faulted circuit and minimizing the risk of electrical shock or fire. When considering solid versus stranded conductors for bonding jumpers, several factors come into play. Firstly, conductivity. Solid conductors generally offer slightly better conductivity than stranded conductors of the same gauge. This is because the stranding process introduces small air gaps between the individual strands, which slightly reduces the overall cross-sectional area available for current flow. Secondly, mechanical strength and durability. Solid conductors are more resistant to breakage and corrosion, especially in harsh environments. The individual strands in a stranded conductor can be susceptible to corrosion at the points where they contact each other, and the strands can also break due to repeated bending or vibration. Thirdly, flexibility and ease of installation. Stranded conductors are more flexible than solid conductors, making them easier to install in tight spaces or where frequent bending is required. However, this flexibility comes at the expense of reduced mechanical strength. Fourthly, safety. A broken bonding jumper can create a hazardous condition as it can interrupt the low impedance path for fault current. This can prevent the overcurrent protective device from operating properly, which can increase the risk of electrical shock or fire. In the context of hydromassage tubs, the bonding jumper connects all metal piping systems, metal parts of electrical equipment, and pump motors associated with the tub. This ensures that all these metal parts are at the same electrical potential. If a fault occurs, such as a live wire coming into contact with a metal part, the bonding jumper will provide a low impedance path for the fault current to flow back to the source, tripping the breaker and de-energizing the circuit. Now, let's consider the specific arguments presented in the proposals. The argument for Proposal 1, which mandates a solid conductor, is that it aligns with the intent of the code and provides a more enforceable requirement. By specifying a solid conductor, the code eliminates any ambiguity and ensures that installers use the type of conductor that is deemed most suitable for the application. The argument against Proposal 2, which removes the word solid, is that it could compromise safety by allowing the use of stranded conductors. Stranded conductors are more likely to break than solid conductors, especially in environments where they are subjected to vibration or repeated bending. A broken bonding jumper can create a hazardous condition as it can interrupt the low impedance path for fault current. From an electrical engineering perspective, the choice between solid and stranded conductors for bonding jumpers depends on the specific application and the environmental condition. In applications where mechanical strength and durability are paramount, solid conductors are generally preferred. In applications where flexibility and ease of installation are more important, stranded conductors may be acceptable, provided that they are properly sized and installed to ensure that they can withstand the expected mechanical stresses. In the case of hydromassage tubs, the environment can be considered relatively harsh due to the presence of moisture and vibration from the pump motor. Therefore, a solid conductor may be a more suitable choice for the bonding jumper. Moreover, the safety implications of a broken bonding jumper in a hydromassage tub are significant, as it could expose users to the risk of electrical shock. For these reasons, it is generally recommended to use solid conductors for bonding jumpers in hydromassage tubs. However, it is important to note that stranded conductors can be used if they are properly sized and installed, and if they are inspected regularly to ensure that they are in good condition. Now, let's delve further into the relevant sections of the National Electrical Code that pertain to bonding and grounding. Article 250 of the NEC provides the general requirements for grounding and bonding. Section 250.4 addresses the general requirements for grounding and bonding of electrical systems. It emphasizes the importance of creating a low-impedance path for fault current to facilitate the operation of overcurrent protective devices. Section 250.8 specifies the methods of grounding and bonding. It allows for the use of various types of conductors, including copper, aluminum, and copper-clad aluminum. It also specifies the minimum size requirements for grounding and bonding conductors, which are based on the size of the overcurrent protective device protecting the circuit. Section 250.92 specifically addresses bonding of metal piping systems and grounded metal parts. It requires that all metal piping systems and grounded metal parts be bonded together to create an electrically continuous path. This is to prevent the buildup of static electricity and to provide a low-impedance path for fault current. Section 680 provides specific requirements for swimming pools, fountains, and similar installations. As previously mentioned, Section 680.74 addresses the bonding requirements for hydromassage tubs. In addition to the bonding requirements, it is also important to ensure that the electrical equipment associated with hydromassage tubs is properly grounded. Grounding provides a path for fault current to flow back to the source in the event of a ground fault. This helps to protect people from electrical shock and to prevent damage to equipment. The grounding conductor must be properly sized and connected to a grounding electrode, such as a ground rod or a metal water pipe. It is also important to ensure that all electrical connections are made properly and that they are protected from moisture and corrosion. Now, let's explore the different types of grounding electrodes that can be used for hydromassage tubs. Section 250.52 of the NEC specifies the types of grounding electrodes that are permitted. These include, firstly, metal underground water pipe. A metal underground water pipe that is in direct contact with the earth for at least 10 feet can be used as a grounding electrode. However, the water pipe must be electrically continuous and it must not have any insulated joints. Secondly, metal frame of the building or structure. The metal frame of a building or structure that is effectively grounded can be used as a grounding electrode. Thirdly, ground rod. A ground rod is a metal rod that is driven into the earth. The ground rod must be at least 8 feet long and it must be made of copper, copper-clad steel, or stainless steel. Fourthly, ground ring. A ground ring is a bare copper conductor that is buried in the earth in a continuous loop. The ground ring must be at least 20 feet long and it must be buried at least 2.5 feet below the surface of the earth. Fifthly, concrete encased electrode. A concrete encased electrode is a bare copper conductor that is encased in concrete. The concrete encased electrode must be at least 20 feet long and it must be located within the bottom 2 inches of a concrete foundation or footing that is in direct contact with the earth. In addition to the grounding electrode, it is also important to have a grounding electrode conductor. The grounding electrode conductor connects the grounding electrode to the equipment grounding bus in the electrical panel. The grounding electrode conductor must be properly sized according to NEC Table 250.66 and it must be protected from physical damage. The equipment grounding conductor provides a path for fault current to flow back to the source from the equipment. The equipment grounding conductor must be properly sized according to NEC Table 250.122 and it must be connected to the equipment grounding bus in the electrical panel and to the metal parts of the equipment. Now, let's discuss the importance of proper installation techniques for bonding and grounding conductors. Proper installation is essential to ensure that the bonding and grounding system functions effectively and safely. Here are some key installation practices. Firstly, use the correct size conductor. The bonding and grounding conductors must be sized according to the NEC tables to ensure that they can carry the expected fault current. Secondly, make secure connections. All connections must be made tightly and securely to ensure that there is good electrical contact. Use appropriate connectors and tools for the type of conductor being used. Thirdly, protect conductors from damage. Bonding and grounding conductors must be protected from physical damage and corrosion. Use conduit or other protective measures where necessary. Fourthly, avoid sharp bends. Avoid making sharp bends in bonding and grounding conductors, as this can reduce the current carrying capacity. Fifthly, inspect regularly. Bonding and grounding systems should be inspected regularly to ensure that they are in good condition. Check for loose connections, damaged conductors, and corrosion. Now let's address some common misconceptions about bonding and grounding. Firstly, bonding is the same as grounding. Bonding and grounding are related but distinct concepts. Grounding provides a path for fault current to flow back to the source, while bonding ensures that all metal parts are at the same electrical potential. Secondly, any conductor can be used for bonding and grounding. Bonding and grounding conductors must be sized and installed according to the NEC requirements. Not all conductors are suitable for bonding and grounding. Thirdly, bonding and grounding are not important. Bonding and grounding are essential for electrical safety. They help to protect people from electrical shock and to prevent damage to equipment. Fourthly, once a bonding and grounding system is installed, it never needs to be inspected. Bonding and grounding systems should be inspected regularly to ensure that they are in good condition. Loose connections, damaged conductors, and corrosion can compromise the effectiveness of the system. In conclusion, the proposals regarding Article 680.74 of the National Electrical Code highlight the importance of specifying the correct type of conductor for bonding jumpers in hydromassage tubs. While both solid and stranded conductors can be used for bonding, solid conductors offer greater mechanical strength and durability, which makes them a more suitable choice for this application. Proper bonding and grounding are essential for electrical safety, and it is important to follow the NEC requirements to ensure that the system functions effectively and safely. The recommendation is to support Proposal 1, which mandates the use of a solid bonding jumper, as it aligns with the intent of the code and provides a more enforceable requirement.